Hello. Uh, so, Good evening, everyone. Today is the third session of fluid flow operations. So, we are going to start in 2 minutes. I'm going to share the screen first. I hope my screen is visible, right? Okay. Let's start today's session. So, in this session, in this week, Sarah has talked about the basic fluid flows, like what is Lagrangian method, what is Eulerian method, like this. So, I'll be revising very fast the main topics and then we'll shift to the problems. Okay. So what is this Lagrangian approach? So what is the Lagrangian? So these are the different approaches of fluid mechanics. Approaches of fluid mechanics. I think it is visible like this also. So first one is the Lagrangian approach. Okay. So what is that? So here it is basically the particle Lagrangian approach is also called the particle based approach. Particle based approach. That means entire bulk of fluid is separated into particles. So what is happened that entire bulk of fluid is separated into particles. There is no internal motion between the particles and continuum property is valid. there is no internal motion between particles and continuum property is valid. Continuum property is valid. Like, so here what is considered that every fluid is a particle, right? But the second, what is continuum approach, I will come to later. The second one is the Eulerian approach. Second one is the Eulerian approach. What does it mean? It means that every fluid property, every fluid property like your velocity, pressure, density, viscosity, etc. can be expressed as a form of fluid field, as a form of fluid field. So that means every function of fluid, every variable is a function of space and time. That means any variable is a function of space and time, right? Like suppose velocity. So velocity is a function of space and time. Then comes your density. Density is also a function of space and time. So this is called the velocity field. Yes, this is called the fluid field. So every property of the fluid can be expressed as a form of fluid field. But in case of Lagrangian, every property, but in Lagrangian, every property is like a particle. Yeah. So what is continuum? So the assumption of continuum. This means that the fluid is considered as a continuous distribution of matter. Okay, that means there is no molecular spacing between the fluid molecules, negating all the atomic or molecular aspect. Okay, so this condition is called continuum. Now, when this is valid? This is valid only, so this continuum concept is valid only when the characteristic length of the system, that is L, is greater than mean free path of the constituent molecules, that is lambda. So that means, so what is the characteristic length? Characteristic length means, suppose this is a plate, okay, and fluid is passing through it, okay. So this length of the plate is called the characteristic length. In case of pipe, the characteristic length will be D, depending upon the problem, okay. So suppose, so this L has to be greater than lambda. Lambda is the mean free path. Mean free path, you already know that mean free path is the molecular, the path covered by a molecule before a collision with another molecule, right? Like between two collisions, the path a molecule covers is called the mean free path. So this is called the lambda. So this L has to be very greater than the lambda. Then only we can consider the continuum assumption is valid. Also, this has a number. So this lambda by L has a ratio which is called the famous Knudsen number. So lambda by L has to be very less, like less than 0.1, to consider the continuum approach. Okay, so I'm not going to detail, but you just know that this is called the continuum Knudsen number ratio. Okay, so now this is the difference between the Lagrangian and Eulerian approach. Next, what are in the lecture? So this is the basic function you can see here. So this is just u is a rate of change of u, that means velocity is the rate of change of distance, and acceleration is the rate of change of velocity. This is how is this defined, and the resultant velocity is defined by this formula root under u square plus v square plus w square. So these are, now comes the lines of flow. So what is a streamline flow? So it is written that the line where its tangent at each point 1 indicates the direction of fluid at that point. Okay. So basically what it is saying, that suppose this is a streamline. Now what it is saying, that a line in the flow field, a line in the flow field to which the velocity component is always tangential. A line in the flow field to which the velocity component is always tangential. Okay, so suppose this is a velocity path. So here you can see, suppose this is a velocity going, okay, q. This has a unit vector dr, and its local velocity component is in the tangential component is this dr plus v. So the velocity component is always tangential. That means dr cross v is always 0 because there is no perpendicular component in the streamline, right? So what is dr and cross dv? So now if we express, so suppose r is your ui cap, vj cap, and wk cap, then what will be, not r, sorry, this is v, velocity component, and dr component is your dxi cap plus dyj cap plus dz k cap. Now from the dr cross dv equals to 0 irrotational flow. So what it will be? So I cap, j cap, k cap, that is dx, dy, dz, then u, v, w equals to 0. So what it is coming? It is coming as dx by u equals to dy by v equals to dz by w, right? Suppose our velocity profile is a I cap minus a y j cap, where a is greater than 0. Now what will be this? So u is our ax, right? So dx by ax equals to dy by minus ay. What it will be? So it will be like, so this a will be cancelled out. So if we integrate it, it will be ln x by x naught equals to ln y naught by y, right? So what it is coming? It is coming like, x0 y0 equals to xy equals to constant value, right? So you have seen earlier that the profile will be like parabolic profile, like hyperbolic profile, this way, right? So this will go like this. This is your streamline profile, right? So this is the tangential component of the velocity vector. So this is what it is done here. This is called our streamline. So we'll do some example. So here say also it is coming like this, right? So then comes a stream function. So stream function has a particular expression. So you all know that U is del psi del y and V is represented minus del psi del x, right? So it has been taught clearly in the lecture. Next classification comes as the path line. Next classification is path line. So these are all the flow visualization. So if you call it, you can call it like flow visualization. So on four type of flow visualizations are there. First one is the streamline. Second one is the path line. Okay, so what is path line? So this is the actual trajectory followed by a fluid particle. Actual trajectory in a fluid followed by a particle. So suppose there is a dye or a particle given in the fluid and this is actually following the fluid motion. So that trajectory is that and you will get a trajectory out of that, right? So that trajectory is called the path line. So what is the path line equation? Path line equation is simple because you know u. So dx by dt equals to u dy. So it is a time based calculation because you are watching the trajectory of the fluid particle. So it is a time based. That is why the definition is on time based. So at t equals to 0, x at x0, y at y0, and z at z0, right? So so you can understand that x is a function of time, y is also a function of time, z is also a function of time. So now if we take the same example of v, like v equals to ax I cap minus ay j cap, then what it is coming. So again we will take u as, so from the definition we know that dx dt equals to ax, right? So if we integrate it will come dx by, like dx by x, that means ln x equals to at, then x equals to x0, t from t, we are integrating it from 0 time to t time, so it will be ln x from 0 x0 to x, so ln x x0 to x, and it is also from t0 to t, so it will be x equals to x0 e to the power at. Similarly dy dt will be minus ax minus ay, and it will be y equals to y0 e to the power minus at. Now from this two also we can get that x0 y0 equals to xy equals to constant. So it is also getting the similar hyperbolic profile like the streamline, right? Yes. The third one is the straight line. So you'll see from the definition of here only. Yes. So the line formed by a series of fluid particles which pass a certain point in the stream one after another. So the definition is the line formed by a series of fluid particles. So the definition is line formed by a series of particles capturing at the same point. Series of fluid particles which pass a certain point in the stream one after another. Which pass a certain point of the stream one after another. Okay, so from the diagram also you can see that this is a fluid particle, right? And a series of particles are sent into the fluid and it is crossing a certain point one after another, and that line, it is following a parabola kind of line. This is called a straight line, right? Then comes your timeline. So path line is the trace of one particle and straight line is the trace of multiple particles. Okay. So path line, you can see here the path line is represents one particle at multiple snapshot in time. So timeline is narrated by drawing a line through adjacent particles in a flow at any instant of time. So in timeline, time is constant. So basically here, what is timeline? Here time is constant. So at any instant of time, so at any instant of time, the line crossing the line passes through adjacent particles in flow. The line passes through adjacent particles in a flow field is called the timeline, right? So in the case of steady flow, stream path and straight lines are all the same because this is a steady flow. So potential line also comes the line of equal velocity potential. So where if the velocity potential of two lines are equal, this is called the potential line. So these are orthogonal to the stream lines. Potential flow describes the velocity field as the gradient of the scalar function. Okay. So potential flow is characterized as an irrotational velocity field. So we'll go to this kind of equation after that. So similar velocity potential is defined as E equals to del phi del x and V equals to del phi del y. So these are the some of the equation, Cauchy-Riemann equation. There some of the examples are there. So flow net is also the graphical representation of streamlines and perpendicular equipotential lines, because you know that the streamlines and potential lines are perpendicular to each other. So that's why this flow, they are creating a flow net kind of thing, right? So this is the principle of making the turbine runner. Okay. So now comes the different types of displacement field. So like how the transition is happening, how transition means ABCD will go to a different translation means ABCD will go to the different place. So if I draw it, so translation means that this ABCD will move to this place. A dash, B dash, C dash and D dash. It has same size, only the displacement and the position has changed. This is called the translation. Okay. What is rotation? Rotation does not cause any stress since there is no relative motion. Relative motion. Okay. So rotation is with the same position. So suppose this is A, B, C and D. So if the rotation happens, so this will look like this. So now this is B dash, C dash and D dash. This is the rotation. Next comes the distortion and deformation where the stresses are produced. So there are two types of distortion. One is the angular distortion, one is the linear distortion. So in case of linear distortion or deformation, linear distortion or deformation is represented by this. So this is A, B, C, D and its size has changed. So now this has become this A, B dash, C dash and D dash. That means its size has changed. And what about angular one? Angular deformation is like this. So this is your A, B, C, D and you will see this, this, this. So now this is B dash, this is C and this is D dash. Okay. And accordingly, this is C dash. The angle has also been changed. Theta 1, there is angle theta 2. Okay. So this is the angular deformation. Theta 1 is counterclockwise and theta 2 is clockwise. Okay. This is the different types of displacement in fluid. So these are the different general types of fluid flow. So you know that steady flow and unsteady flow. So in case of steady flow, it is not anymore time dependent, right? In case of steady flow it is not varying with time. Unsteady flow it is always varying with time. Uniform non-uniform means it has some material is homogeneous and throughout the fluid, and non-uniform means the flow is inhomogeneous after some point of time, right? Developed flow means that initially there is a boundary condition supposed and then after some time the fluid has fully developed and that it will the gradient of the fluid the gradient velocity will not change anymore. That is du dx equals to 0. That is a developed flow or fully developed flow. Compressible or incompressible fluid means compressible means that the in which the density change with space and time is negligible is called the incompressible flow, right? And compressible flow is where the velocity or density change with space and time is not it is not negligible. So if you find the expression, so incompressible incompressible density, so continuity equation will come to later. So this is 0, and for compressible this is not equals to 0. Okay. Viscous and inviscid flow. Viscous flow means where the viscosity mu is very low, and mu is very low, is called the like inviscid flow, and where you cannot neglect the viscosity effect is called the viscous flow, obviously. Laminar flow means the large layer-wise flow of fluid, like different layers of fluid move relative to one another. So there is a layers of fluid moving one another side by side. They are not mixing up. And turbulent flow means that there is a continuous or chaotic random motion of the fluid velocity component. So I have already discussed this in the earlier classes. So there is a transition zone between the laminar and the turbulent flow. This is called the transitional flow. For different type of fluid, like for pipe flow, the different type of Reynolds number, and this turbulent flow, laminar flow is defined by defined by this Reynolds number, which is the ratio of inertial force to viscous force. So what it is that? So Reynolds number Reynolds number is a ratio of inertial force. This is a very important parameter in fluid. Why? Viscous force. So inertial flow expression is rho v square a, or you can write it as rho v square a basically. Then inertial flow is mu v by L into L square. A can be written also as rho v square L square, because A is the area meter square, mu v by L into L square. Now what is coming? This will cut out. This is 1. So it is coming as rho v L by mu. So this L is your characteristic length. For pipe flow, it is the diameter I have just said, and flow over a flat plate. L is this distance of the plate. Okay. So it will vary according to your geometry of the system. So this is the important number, and this number varies from laminar zone to transition zone to turbulent zone. For in case of pipe flow, so in case of pipe flow, for pipe flow, suppose this is your Reynolds number zone. So this is the RE1 zone, this is RE2 zone. So this is your laminar zone. This is your transition zone, and this is your turbulent zone. Okay. So what is happening for pipe flow? This laminar, this value is around RE1 value is around 2100, and RE2 turbulent zone value is 4000. But if you find research paper, they call it that exact turbulent point where the transition happens in a pipe flow from stable flow to instable flow is exact value of RE is 5772. Okay. For flow over a flat plate, this RE1 is 5 into 10 to the power 5 and RE2 is around 10 to the power 7. Okay. So this is for the theoretical. These are the theoretical values. Okay. Next, what comes? Next comes the one-dimensional, two-dimensional, and three-dimensional values, flows. So 1D flow means 1D flow means there is only one direction. That is that there is only one number of independent space coordinate present. Right? So here, suppose there is a pipe flow and the velocity is changing in the x direction. So here v is a function of only x. This is 1D flow. In case of 2D flow, so the direction is changing, the fluid flow is changing in both the direction. Okay, so here you can see that the fluid velocity is like this, but here the fluid velocity is little bit changed. So now this v, or you can, if it is a center line, you can call it r or x, whatever. So now you can see that v is a function of r and z. So velocity is changing both in the r direction and z direction. And 3D flow, in case of 3D flow, you can see that it is changing in the shape also. So if this is r and z direction, so this v is a function of r, theta and z also. So these are the different types of flow. Next comes the rotational or rotational flow. Rotational flow and irrotational flow is represented by the omega, right? Subcritical and supercritical flow and subsonic, sonic and supersonic flow. So these are the basic things learned. So here the definitions are given. I have already described. Now I am not going to this anymore. And in the lecture 6, it is mostly about this flow, acceleration, so you have known that v is a function of suppose x, y, z and t, and now comes the acceleration. So this again divide by dt. So from there you will got your acceleration. So sorry for the network disruption. So now I have come back again. So this is the acceleration part. Okay. So now this. So what I am saying that again, if I have to do this like v is a function of x, y, z and t, right? So dv equals to del v del x dx plus del v del y dy plus del v del z dz plus del v del t dt. And if you want a, that means a is dv dt, that is all of the terms will be divided by dt. So it will be del v del x to dx dt plus del v del y dy dt plus del v del z dz dt plus del v del t, right? And now you know that dx dt is nothing but your u. So u del v del x plus v del v del y plus w del v del z plus del v del t. So this is called your convective acceleration, right? And this is your local acceleration, right? And based on this, we will do some problem. So I'm not going further. So it is already given. So there are basic definitions. So when we are writing like del v del x, right? So this is your partial time derivative. Suppose so what is the definition of partial time derivative? So partial time derivative is like, suppose we stand on a bridge and observe the concentration of fish just below us as a function of time. So we are observing something when we are standing at the same place, and we are observing the change of that variable with respect to time, right? This is your partial time derivative. Now what is the total time derivative? That is d dt. So small d dt. Okay, now suppose we jump into a motor boat and speed around on the river, sometimes going upstream, sometimes downstream, and sometimes across the current. All the time we are observing fish concentration. So when we are in a motion along with the variable that is captured by the total time derivative is represented by d dt, and substantial time derivative capital DDT is the next. We just float along the current observing the fish concentration. That means we are only following the current. In the previous case of total derivative, we are going anywhere along the current, opposite to the current, like that. But in case of total substantial time derivative, we are along the current. So this is how it is represented. So this dc here, it is represented as a concentration. If you think as a velocity also, you can think that. So if you write this in terms of velocities, what it will be? So dv dt, total time derivative, just now, just like this expression, right? So dv dt equals to del v del t. You have written it, right? You have written it here. Del v del t plus del v del x into del x del t. So del v del x into, so all these are a function of x, y, z, plus del dx dt into del v del x plus dy dt equals to del v del y and plus dz dt into del v del z. So this is your total derivative. And substantial time derivative is, so this total thing can be represented as a substantial time derivative. So here if we write it like this, so here also it is written, right? Now this A is represented by this, right? So this is your total derivative. Total derivative, if you write like in case of V, so dV dt equals to del V del t plus U del V del x plus V del V del y plus W del V del z, or dV dt is del V del t plus V into V divergence of gradient of V. Okay. So this is your local acceleration term. This is your convective acceleration term. Okay. Okay. Now we are done, or anything else is left here. So this can be done in case of pressure term also, or density term also, all the way. Okay. So this is the rotation and spinning of liquid. So this is the calculation of rotational velocity. So here you'll see the final, you can see it from the lecture. So final expression is like this: vorticity omega z del v del x minus del u del y. Similarly, you have got the other components also, and vorticity vector is the twice of the rotational angular velocity. So for rotational, for angular velocity and vorticity will be 0. Okay. So this is your problem. This is a circular structure. You can go through it. Then this is the last portion. Okay. Now we'll solve some equations or some problems for you to solve the this week's assignment. So, which of the following lines of flow are formed by a series of particles passing through a particular Eulerian point in the stream? So we have just learnt in this class that streamline is a line where the velocity vector is tangential. Path line is the trajectory of single particle. So streak line is the, so if you go through the definition, so this streak line is the line formed by a series of particles which pass a certain point of the stream one after another. So this definition matches with the streak line. Okay. Next. Potential flow theory cannot be applied to which of the following flows? So potential flow theory can be applied in irrotational flows. It can be applied in incompressible flows, but it cannot be applied in viscous internal flows. Next, a flow net is a graphic representation of, we have seen that flow net, these are the supposed streamlines and these are the potential lines, right? This is your streamlines and this is your equipotential lines. So it is the streamline and perpendicular potential line. Option D. Next, a fluid flows in a pipe of diameter d at a velocity u. What will happen to Reynolds number if the diameter of the pipe is reduced to half and the velocity is increased to 4 times the original value? So what is written? The Reynolds number RE is, so in case of pipe, it is the characteristic length is diameter, rho Vd by mu. So now what it is said, that diameter of the pipe is reduced to half. So now rho and mu will be at it as it is. V is increased 4 times. So that will be 4V, and sorry, prime is new one, 4V, and density is diameter is half. So it is d by 2. So what is rho 4 rho V d by 2 mu, right? So 2 will be cancelled out. So it will be 2 into rho Vd by mu. It is 2 into Re. So it will be, Re becomes twice the original value, right? Yes. The transition from laminar to turbulent flow in a pipe does not depend on what? So the fifth question is, the transition from laminar to turbulent flow in a pipe does not depend on what? So this transition from laminar to turbulent flow is always dependent on the Reynolds number, right? So Re equals to rho Vd by mu. So it does depend on diameter, it does depend on the density of fluid, not the density of pipe, right? So the answer will be, it obviously depends on the velocity of the fluid. So it is the density of the pipe. Right answer is option B. Next, which of the following is not true regarding developed flows? The velocity profiles don't change with respect to the flow direction. The momentum does not change with respect to the downstream coordinate. The flow cannot be time dependent. The pressure in the flow direction balances the shear stress at the wall. Which one is true? Tell me. Fully developed flow means the velocity profile does not change anymore with the flow direction. The momentum also does not change, but it can be time dependent. So it is option C is not true for this case. Next. In which type of flow does the velocity not vary at every point and in space at any given instant? So steady flow means it doesn't vary with time, but it doesn't guarantee that it will not vary with space. So it is not a steady flow. It is the uniform flow. Uniform flow means at any given instant the velocity does not vary at every point in space. So answer is uniform flow. Next. In case of large Reynolds number, inertial forces will be dominant, viscous forces will be dominant, the flow will be laminar, none of the above. What is true? Tell me. I'm giving time because I have told what is the definition of Reynolds number. From there only you can tell this. So, Reynolds number is the ratio of inertial force versus Viscous force, right? So if Reynolds number, if it is large Reynolds number, that means inertial force is high. So inertial force will be dominant. Now, in the case of velocity field given, where A and B are also given, find the equation of the streamlines where X, Y, V and C are defined. So it is called the find the equation of streamlines, right? So what it is written, V is ax cube I cap plus bxy cube j cap, right? So here u equals to ax cube and v equals to bxy cube, right? So now you know the equation, streamline equation, right? The streamline equation is dx by u equals to dy by v. So it is coming as dx by ax cube equals to dy by bxy cube. And a and b has values, right? A is 2 and b is 2. So this is dx by 2x cube equals to dy by 2xy cube. So 2 will be cancelled out. So what it is that? Dx by x cube equals to dy by xy cube, right? So now dx by x square equals to dy by y cube. Now the integration will happen. What is the integration? Right? This will be the integration. So remember, like x to the power minus 2 dx. So what it is that? Minus x to the power minus 1 equals to minus like y to the power minus 3 plus 1, that is minus 2 divided by minus 2 plus c, right? So what it is? It is like minus 1 by x equals to minus 1 by 2y square plus c. So what is coming? Like 1 by x equals to 1 by 2y square plus c prime equals to 1 by 2y square equals to 1 minus x minus 1 by x minus c prime. So next comes 2y square. 2y square equals to 1 by x minus c prime. So y square equals to 1 by 2 into 1 by x minus c prime, and y equals to root under 1 by 2 into 1 by x minus c prime. Is this coming? Is it there? Y equals to 1 by 2 into 1 by x. So yes, so this is option B, right? This is option B. Next, identify the correct form of the Cauchy-Riemann equations for the velocity field. This is a velocity field. Everything is defined. So Cauchy-Riemann's for stream function and the potential line. So we know that for stream function u equals to del psi del y, and this is for stream function. And for potential function u equals to del phi del x. Here v equals to minus del psi del x and v equals to del phi del y. So where is correct? Like it is the option 1, I think. Equals to del phi del x del psi del y, v equals to del phi del y equals to minus del phi del x. Yes, it is option A. Next. What is the range of Reynolds number for transition region for flow in pipes? So we have discussed it. It is around between the 2300 to 4000. Next. The dash is a measure of the rotation of a fluid element as it moves in the flow field. So it is the vorticity. It is the vorticity. That is omega. It is defined as half of curl V. Next. The velocity components at a point in a flow are given as this. Determine the vorticity. Right? So it is coming. So the vorticity omega x. So we have just seen the expression of vorticity, right? Omega equals to curl of V, half of curl of V. So now, so omega x component. So curl of V, if we do it, so curl of V means in this case it is the I cap, j cap, k cap, del del x, del del y, del del z, u v w, right? Equals to del v del x minus, sorry, it is del w, so it is del w del y minus del v del z I cap plus del u del z minus del w del x j cap plus del v del x minus del u del y k cap, right? So we have to find this components first. So vorticity x component is del w del y minus del v del z equals to Del W del Y means minus 6 minus del V del Z minus 8. That is minus 6 plus 8 is plus 2. Next, vorticity Y component is del U del Z minus del W del X. Del U del Z minus del W del X. So del U del Z means minus 3 minus del W del X is plus 7. It is 7. So it is minus 10. And WZ component is del V del X minus del U del Y. Del V del X minus del U del Y equals to del V del X 6 minus 6 minus 6 minus del U del Y means plus 2. Plus 2. It is minus 8. Okay. So now the resultant omega will come as omega x square plus omega x square plus omega y square plus omega z square. So it is the 2 square plus minus 10 square plus minus 8 square is coming as 4 plus 100 plus 64 root under this means 12.96. So is the answer is there? 12.96, yes. So it is option D. It is coming as 12.96 radian per second. Next, circulation is the surface integral of velocity, the gradient of vorticity, the surface integral of vorticity, and the gradient of velocity. So, from definition, the circulation is the surface integral of the vorticity. So, it is option C. Next, acceleration is depicted as dv dt, where v is the velocity vector. What does d dt mean? D dt is the material derivative or substantial derivative or substantial derivative. Next, consider the following velocity vector where the coordinates are measured in meters and time in seconds. Find the convective acceleration at the point 2, 2. Okay, do it. So convective acceleration means AX is U del V del X plus or U del X plus V del U del Y AY is as it is a 2D flow, so it is V del U del X plus V del V del Y, right? So now you calculate. So AX is, so velocity component at 2 point means u is -2 plus 2 into time 2. So it is 4 minus 2, 2 meter per second. And v is, y is again 2 plus 2 into 2. This is 4 plus 2 is 6 meter per second. Now comes the ax. So ax is, u is 2, del u del x from the expression is -1, right? Plus v is 6 and del u del y is 0, equals to -2 meter square, meter per second square, sorry, meter per second square. Ay equals to v means 6 into del u del x, sorry, del v del x, del v del x, that is also 0, plus uh, 6 into, this is 2 into u into del v del x, right? So this is u into del v del x. It is 2 into 0. This is 6 into del v del y is 1. So it is again 6 meter per second square. So the convective acceleration term A is root over ax square plus az square equals to, it is coming as -2 square, that means 4 plus 6 square 36. That is 6.32 meter per second square. So that is option B. That is your option B. Next, which of the following statements are not true? The angular velocity is twice of the vorticity. It is true, right? Sorry, it is not true. The angular velocity is twice of the vorticity is not true. The opposite one is this. The vorticity omega is the twice of the angular velocity. That is true. The vorticity is 0 for irrotational flow. This is true. The vorticity in a closed curve is 0. It is also true. All the so first one is the correct answer here. Next, pick the correct expression. So dv dt, u del v del t, no, dv dt is u del v del x plus v del v del y plus w del v del z plus del v del t. This is the option C. Right? This is the expression of total derivative. Next. If v is the velocity, represents the velocity vector, how would you obtain the local acceleration? The local acceleration is the del v del t. Option A. Next, the velocity field is given as this. What should be the z component of the vorticity? So from the equation itself, we have found that z component of the vorticity will be this. So from here only we have given, if you do the curl, here, right? So it is the z component, right? If del del z term is not there and w is 0, so this will be only remaining the term, right? So this is the z component. So this is the del u. So from there only you can, so suppose if I am doing it again, so it is curl of v, it is I cap, j cap, k cap is there, plus d dx, d dy, d dz, or del. Here it is u, v, but w term is not there. It is also not here, so it is also 0, it is also 0. So only the k term will be remaining. So it is the del v del x minus del u del y. Del u del y. Okay. So this is the z component term. Option B. Next, now I'll do some more mathematical problems. So now tell which method of describing fluid motion focuses on the behavior of individual fluid particles. So from the definition itself, we have learnt at the first or at the beginning of this session that what is Eulerian and Lagrangian. So Lagrangian mostly deals with the individual fluid particles as they move through space and time, but Eulerian thinks it as a flow field. So the first answer is Lagrangian method. Next, a streamline is defined as a line where the tangent at any point indicates the magnitude of acceleration, the pressure gradient, the direction of fluid flow velocity at that point, and the density of the bed. So it is obviously the fluid flow local velocity, that is the fluid flow velocity at that point. Next, in which type of flow are streamlines, path lines, and straight lines all are identical? So it is the steady flow. Next, the Reynolds number is a dimensionless ratio that compares which two types of forces. I have done it multiple times, so it is the inertial force by viscous force. According to Stokes' theorem, circulation is mathematically equal to the product of velocity and distance, pressure and area, vorticity and area, density and volume. So it is the vorticity and area. Option C. So this is vorticity omega into A. Next, a two-dimensional flow field is defined by the velocity components. Calculate the resultant velocity and the components of convective acceleration at the point 1 and 2. So very easy. So velocity components will be easily coming. So u equals to 2 into 1 square means 2 meter per second or units per second, and v is the minus 4 into 1 into 2, so this is minus 8 unit per second. So these are the components of velocity. So what will be the resultant velocity? So resultant velocity will be 2 square plus minus 8 square equals to 8.24 unit per second. Yes. So this is one of the answers. And second one is the convective acceleration at that point. So convective acceleration will come from the ax. So ax is u into del u del x plus v into del u del y. So u is 2, del u del x means 4x plus v is minus 8 and del u del y is 0, right? So this is 2 into 4x means 2 into 4, that is 8 unit per second square. And ay is similarly u into del v del x plus v into del v del y equals to u is 2, del v del x is minus 4y plus v is minus 8, del v del y is minus 4x equals to, so this is y is 2, so minus 16 minus 32, like plus 32, sorry. So this is 16 unit per second square. So this is your components of convective accelerations, right? Next problem. Given a stream function, find the velocity components at the resultant velocity at point this. So psi is 2x square minus y square. So u equals to del psi del x. This is stream function. U equals u equals to del psi del y. So del psi del y means minus 2y, that is minus 2 into 3, that is minus 6. V equals to del psi minus del psi del x equals to minus, this is 4x equals to 4 into 2, that is minus 8, right? So now these are the individual velocity components, and resultant velocity means v equals to root over minus 6 square plus minus 8 square equals to 10 unit per second square, or second, sorry. This is your answer. Next, a fluid flow is described by U and V. Determine the vorticity and the circulation around the square area defined by X and Y. So as this has U component and V component, then the vorticity component will always be in the Z direction. So your omega Z component is del V del X minus del U del Y equals to del V del X is 0 minus del U del Y is 3. So this is minus 3. Vorticity is minus 3 radian per second, and the circulation is omega Z into A, right? So omega Z is minus 3, and area is defined as square area, like x equals to 2, y equals to 2. This is 2 into 2. So this is minus 12. So this is here circulation. Okay. Next, the local acceleration term in a fluid flow expression specifically refers to the change in velocity due to change in position, the change in velocity with respect to time at a fixed position, the acceleration occurring within the boundary layer only, the resultant of the xyz velocity components. So it is the velocity. It is option B. The change in velocity. So from the definition only it is clear that when we have written dv, this is del v del x at constant y, z and t dx plus del v del y at constant x, z, t into dy plus del v del z at constant x, y and t to dz plus del v del t at constant x, y and z. So this term finally into dt. So this term is finally going into the local acceleration contribution. So it is at the change in velocity with respect to time at a fixed position. Next. Which of the following equations represent the Cauchy-Riemann relationship between velocity potential and stream function? So you already know that u is del phi del x, del psi del y, v is del phi del y minus del psi del x. So this is option A. Next. If a fluid element undergoes pure rotation, what is the physical implication regarding the internal stress? Stresses are maximized at the pivot point. It causes linear distortion and volume change. It does not cause any stress because there is no relative motion with respect to the rotating system. Stresses are only produced if the flow is turbulent. So what do you think? It is the option C. So we have seen that, right? What is rotation? So rotation means this will go to this. So this is, it does not cause any stress because there is no relative motion with respect to the rotating system. Next, a two-dimensional flow is situated such that the velocity components are this. Find the circulation about the circle defined by this, where A is the radius. So the omega z component is del v del x minus del u del y equals to 0 minus k equals to minus k, right? Then the determination of area. So this is a circle, right? A is the radius. So A equals to pi a square. Then the circulation is just omega into A or omega z into A, and it will be minus k pi a square. So this is your answer. Next, given the velocity components is this, determine if the flow is irrotational. So you have known the terms of vorticity components from the previous case. I am not deriving again. So I am just writing omega x equals to Yeah, it is omega equals to half of curl V, right? Always. So omega x is half of del W del Y minus del V del Z equals to half of del W del Y is minus E minus del V del Z is again minus E. So minus E plus E equals to 0. Omega Y equals to, just a minute. Oh, this is the vorticity. We have calculated the vorticity for this because that is why we have not divided by U. But here we are calculating the angular velocity, right? So angular velocity relation is this. So angular velocity is omega equals to 2 into this, right? So this is that is high. So omega y equals to half of del u del z minus del w del x. I had a confusion, that is why I checked it. Okay. So now half into del u del z means minus c and minus del w del x means c. So it is minus 2c by 2, that is minus c. Next wz equals to half of del v del x minus del u del y equals to half of del v del x is minus b del u del y is b. So it is again minus b. So angular velocity is coming as the summation of all these things. So it is coming as b square plus c square. Okay. So we know that b square plus c square root under it is always positive. It cannot be zero. So it is not an irrotational flow. It is a rotational flow. So the flow is rotational. It proves flow is rotational. Next. A stream function is given by this. Find the corresponding velocity functions. Velocity potential function. Stream function is this and find the velocity potential functions. Okay. So u is stream function. So del psi del y equals to minus 6y. V is minus del psi del x equals to 6x. Right? And potential function is u equals to del phi del x, which is u is minus 6y, right? That means phi equals to minus 6xy plus c, and v equals to del phi del y equals to 6x. That means phi equals to 6xy. Oh, there's a minus, I missed it. Okay. This is minus, so minus 6xy plus c dash. So comparing both, so this is the final expression. Phi equals to minus 6y plus c or c double prime, whatever it is. Next, a velocity potential function for a two-dimensional flow is given by this. Determine the velocity components, find the corresponding stream function, and verify if the flow is rotational. So you have to do everything here, right? So u equals to, this is the potential function is given. So u equals to del phi del x equals to 2x and v equals to del phi del y equals to minus 2y. These are the velocity components. Find the corresponding stream function. So u equals to del psi del y equals to 2x. That means psi equals to 2xy plus c and v equals to minus del psi del x equals to minus 2y. That means psi equals to 2xy plus c prime. So this is your corresponding stream function. And verify if the flow is irrotational. So from the definition we can say that we know that flow is defined by a velocity potential. It is by definition irrotational. So fluid flow is defined by fluid flow is defined by velocity potential function. So from definition, so by definition, it is irrotational flow. That means angular velocity and vorticity will be zero. Or if you want to prove, you can prove how that you know that now the velocity vector will be 2x I cap minus 2y j cap, right? Yes. So from omega z component will be del v del x minus del u del y. Del v del x is 0 minus 0, it is 0. Omega z is 0, that means this is also 0, so it is irrotational. A fluid flows through a 3D space where the velocity field is this. Calculate total acceleration components and x, y, and t. Okay. So total acceleration you have to calculate, right? So ax is u del x plus v del u del y plus del u del t equals to, so u component is known, that is x plus t, or you can do it earlier, u is x plus t, that is 1 plus 1 2, v is y, that is 2, and you don't need the z component, it is 0. So u is 2, del u del x is 1 plus v is 2, del u del y is 0 plus del u del t is also 1. So it is coming as 2 plus 1, 3. Then ay, it is similarly u into del v del x plus v into del v del y plus del v del t equals to, u is 2, del v del x is 0 plus 2, del v del y is 1 plus del v del t is 0. So it is coming as 2. So these are the components. Next, a fluid rotates with an angular velocity. This find the vorticity and the circulation around a circle of radius r equals to 2 meters. So from the relation we know that angular velocity vorticity is twice of the angular velocity, so it is 2 into 5 10 radian per second. Then comes the circulation is omega z a. So for circle of radius it is 10 into pi r square. So this is 10 into pi 2 square is 4 pi equals to 40 pi equals to, or you can write pi. So it is coming as 125.66 meter square per second. Next question. Given a pressure field where h is a constant height and p varies with time t, if a fluid particle moves with velocity w in the z direction, find the substantial derivative dp dt. The substantial derivative dp dt will be u del p del x plus v del p del y plus z del p del z plus del p del t equals to, there is no velocity component of u, so it is 0, it is also 0, so z direction velocity component, this is w. So w del p del z is minus rho g plus del p del t is p. So this is p minus rho g w. Okay, answer. This is a substantial derivative. Next, in a two-dimensional flow, the velocity components are given by this. Determine the equation of streamline passing through the point 1 and 2. So streamline equation of streamline. So dm equation means dx by u equals to dy by v. That means dx by 2x equals to dy by minus 2y. So it is coming as dx by x equals to minus dy by y. So integrating, it is coming ln x equals to minus ln y plus ln c. Right? So it is coming ln xy equals to ln c. So it is coming as xy equals to c. So xy equals to c means c equals to therefore 2. So the equation is ln xy equals to 2. So this is your answer. Next, a fluid flows through a path where u equals to 10 by x and v equals to 0. Calculate the total acceleration at x equals to 2. So total acceleration is, so it has x component, ax equals to u del x plus V del u del y. It is talking about the total acceleration, right? Yeah. So equals to, so it doesn't have t terms, so I'm not writing the t. So it is u. So u is already given, like u equals to 10 by x means 10 by 2, 5. So 5 into del u del x. So del u del x is minus 10 x to the power minus 2 plus v is 0. So it is coming as minus 50 x to the power minus 2, right? So it is coming as minus 50 by x square equals to minus 50 by 25. So it is coming as at x equals to 2. Oh, sorry, at x equals to 2. I thought x equals to 5. It is x equals to 2 means 4. So it is coming as minus 12.5. So that is your total acceleration because it doesn't have a y component because v is 0, right? So anyway, it doesn't count. Next, given u equals to 4x and v equals to 4y, find velocity potential function. So u equals to velocity potential function. So u equals to del phi del x equals to 4x. So phi is 4x del x, that is 4 by 2 x square plus c equals to 2x square plus c. Then v equals to del phi del y equals to minus 4y. So phi equals to minus 4 by 2 y square plus c prime equals to, is it? Okay. So this c will be always a function of y, right? Because it is coming from the potential function. So c is a function of y. So we will put the values. So del phi del y now is del phi del y from the previous one, it is f dash y, only f dash y equals to minus 4y. So now if we integrate f dash y, so it is coming as fy equals to, f dash y means del f del y, right? It is coming as minus 4 by 2y square plus c. Or you can do it the next, that fy is minus 4 by 2 y square plus c, or function of x. So this is minus 2y square plus fx. Also, what can we do from the previous one also? So here also it is coming as like phi equals to minus 2y square plus c. Another approach I am telling, c prime. So this final potential function is 2x square minus 2y square plus c. So this is your answer. Next, a flow has a velocity potential this, calculate the vorticity component. So vorticity component omega z is del v del x minus del u del y. Del v del x is 0 minus 5 equals to minus 5. So this is the vorticity component. Next, for the flow u and u is 2I, we calculate the circulation. So we know the omega is del v del y, that is del v del x, that is 3 minus del u del y, that is 2, that is 1. So this circulation is 1 into, I have not writing the equation again because I have done it multiple times earlier. So the square. So this is 0, 0, 1, 0, 1, 0. This is 1, 1 and 0, 1. So this is a 1 into 1 square. This is 1. This is your circulation. Next, water flows through a pipe of diameter at a velocity, but if the flow is laminar or turbulent. So RE is rho is 1000 into V is 0.1, diameter is 0.05 divided by 0.001 Pascal per second. So RE is coming as 50,000, right? How come? 1000 into 0.1 into 0.05 divided by 0.001, which is coming as 5,000, sorry. So this is greater than 4,000 slightly, so it is turbulent. Next, in unsteady compressible flow, the density is given as this. If U equals to 2, find the substantial derivative d rho dt. So d rho dt means U into del rho del x plus V into del rho del y plus Z in W into del rho del z plus del rho del t. So U is 2, del rho del x is there, so it is rho 0 e to the power minus t sin x, derivative is cos x. Del rho del y, not, it is not a function of y and z, so leave it. So del rho del t is minus rho 0 e to the power minus t sin x. So what is coming? It is just coming like this. 2, if we common it, 2 rho 0 e to the power minus t. So it is 2 cos x minus sin x. Okay. Next, if phi equals to xy, then find psi and prove they are orthogonal. Okay. So phi equals to xy, that means u equals to del phi del x equals to y, y equals to, sorry, v equals to del phi del y equals to x, right? Then psi equals to then u equals to, for stream function, u equals to del psi del y equals to y. So psi is y square plus half of half y square plus f of x, and v equals to minus del psi del x equals to x equals to psi equals to minus, therefore psi equals to minus half x square plus fy. So this, now the psi function is half into y square minus x square plus c. Okay, so proof would be del phi del x into del psi del x plus del phi del y into del psi del y equals to, so del phi del x is y, del psi del x is minus x plus del phi del y is x and del psi del y is y again. So it is plus y minus y equals to 0. So they are orthogonal. Next, a string tube has a cross-sectional area that decreases from A1 to A2 if the velocity at the inlet is 2, and find the velocity at the outlet for the incompressible flow. So it is A1 into V1 equals to A2 into V2, you know. So it is 0.5 into 2 equals to 0.2 into V2. So it will be coming as, V2 will be coming as 5 meter per second. So it will be increased. Next, a 3D flow field is given by this. Calculate the resultant angular velocity. So resultant angular velocity omega x is half of del w del y minus del v del z. So equals to half into del w del y is 0, del v del z is 1. It is coming minus 0.5. Y component is del u del z minus del w del x equals to half del u del z is 0 minus del w del x is 1. So it is again minus 0.5. Omega z is half into del v del x minus del u del y equals to half of del v del x is 0 and del u del y is 1, again it is minus 0.5. So omega is, resultant angular velocity is summation of all this under root 0.5 square plus 0.5 square plus 0.5 square. So it is 0.866 radian per second. So that's it for today. I hope you will find all these problems and discussions, earlier discussions, helpful for solving your this week assignment and overall understanding of the flow field. Okay, till then, goodbye.